studying mechanical engineering, and my background is in sound engineering and IT system administration. But the reason I returned to education was because I found out about these devices, these proposed solutions for nuclear energy called Molten Salt Reactors. And there's a whole bunch of proposed benefits, or claimed benefits, of these systems, which got me interested in them. The enhanced safety, certainly, is one of them. So, unlike the existing nuclear stations, which are prone to overheating and spreading all sorts of radioactive gases everywhere, these ones apparently don't do that. I thought, sounds interesting, let's look into that. So various different kind of fuel configurations we have as well. So we have spent nuclear fuel, we can use thorium, or we can use existing enriched uranium, which the current industry uses. Talk about high fuel efficiency as well. So typically over 90% fuel burn-up. Low weapons proliferation potential. So reduced likelihood of people making big weapons out of them. Process heat generation as well. So these systems produce so much heat that we can actually start using other systems such as desalination, cement manufacture, other sort of things which typically we would need more fuel to put into them as well. Reduce capital costs as well. Capital costs really is the driving cost of nuclear energy, because there are so many safety systems involved. Then building the plant up front is the main driving cost. Fuel itself through maintenance is fairly negligible, well not negligible, but it's a lot lower in comparison with that. With these systems, we can build them a lot cheaper, which means that they're economical and will be driven by market forces. Flexible locations as well. Unlike traditional reactors, which generally need to be located near water, quite often these things are purported to be able to be put in various locations. So you put one out in the middle of the desert, doesn't need access to water because it's full of the chemicals that it already needs. Mass production as well is another feature where we can actually build these things in a factory and then ship them out to a location where they just need to be assembled. And other things like saleable fission products, because of the chemical processing which is involved, we can actually we can siphon off some of these fission products and use them for things like manufacture or medical applications as well. So I was lucky enough to be involved with this study last year, which came out July 2015, with energy process developments. The study was called Feasibility of Developing a Pilot-Scale Molten Salt Reactor in the UK. And we worked with Fraser Nash Consultants and Atkins, who worked on technical and economical appraisals. And we were also in touch with Oak Ridge National Laboratory, who are one of the leading nuclear research facilities in the world. We're responsible for the Manhattan Project and the first, the USS Nautilus, the first nuclear reactors. So the director there, Dr. Trevor Griffiths, was in fact worked with in Oak Ridge back in the 60s. Jasper Tomlinson was put a lot of funding into this report, and Rory O'Sullivan was the project manager there. The supervisory panel, we've had professors from Cambridge and Oxford University there. Other contributors include David Glasbrook there, who has worked on looking at regulation. And Dr. Horvath there was a nuclear engineer who looked at fuel cycles and such like. We had a whole list of other contributors there. My name would be quite low down on it, but quite a lot of other technical contributions as well. Okay, so I'll just give a bit of background about how we ended up with the nuclear industry that we have today. The USS Nautilus was the first nuclear submarine which was built. Initial estimates were that it was going to take about 30 years to build one of them, and they built it in 4 in the end. That was built at Oak Ridge, or designed at Oak Ridge National Laboratory as well. Then pretty much all they did was they took the core out of that, stuck it on land instead, and with incremental changes, we now have most of the reactors that we have in the world are still very much based on that original sort of core reactor there. Now the advantage, of course, when you're in a submarine, when you need to cool one of these things, is that you have an enormous heat sink because you're in the ocean. and the ocean, of course, plenty of water there to keep it cool. When you're on land, obviously you don't have quite that same luxury, so you need to have all sorts of systems to keep that going, to keep it cooling there, basically. Now, of course, this runs off uranium, which you're probably all familiar with. What you may or may not know is that most naturally occurring uranium occurs with the isotope uranium-238, so that's the atomic mass of 238. Whereas, in fact, in order to get the nuclear reaction starting off, we need uranium-235, which is a very low occurring isotope. Naturally occurs about 0.7% of naturally occurring uranium. So in order to get that, we have this enrichment process. There are several ways of doing it. This is the most popular, using centrifuges. If we were to zoom out on this picture, you'd see that there's hundreds and hundreds of these. So it takes up quite a lot of energy, and we end up with something like this. So fuel pellets there, with a ceramic pellet with uranium fluoride. That ends up going into these sort of fuel rods, which go to fuel assembly, and then these end up in a reactor much like this. Now, this is one particular type of light water reactor. There are many others. This will do for the purpose of illustration, but we can see what happens here is that the fuel rods are here, solid fuel rods, they sit there, and then water is pumped around here, which acts as a moderator and as a coolant. I'll get on to what moderator is in a minute. But for the meantime, you can see that these fuel elements, there's the colour gradient there represents the temperature gradient, because there is actually quite a significant difference in temperature, not only as you can see vertically here, but also within the pellets themselves. The centre of the fuel pellet is actually significantly hotter than the outside, because it's not particularly a good conductor. So there's a very large temperature gradient there. Just for completeness, in the UK, of course, we have these different kind of reactors, advanced gas-cooled ones. Similar sort of system, but the coolant is pumping around here is carbon dioxide. Now, most of the ones in the world are light water reactors. Now, you can imagine if something happens whereby this pipe splits here, then certainly, you don't want to be standing here, because that's about 160 bar, it's a few hundred degrees centigrade, and you will end up looking a bit like a lobster. But also, within the core, we have this situation where we now, it's so hot that we have the water starts disassociating. So we now have hydrogen, oxygen, high temperatures, and a whole lot of dangerous radioactive gases. So this is very much a situation we want to avoid. So not shown in this simple schematic is a whole bunch of redundant systems to make sure that we don't end up with this situation, because that's not what we want. Now, of course, as we know, sometimes, like in Fukushima, for example, when power's been knocked out completely, then there's nothing left to power the redundant systems, and things can go wrong. There are, of course, other ways of doing it where these things don't go wrong, but these all add to the expense in the first place. Now, if we look as well at the top right here, we can see that after a while the fuel pellets start cracking as well. And the problem is when they start cracking is we start releasing dangerous gases into the environment as well, or the environment of the core. So they are hard to keep contained. So here we have a graph, again, we're just explaining a bit of the background behind how this all works, for those of you who are not familiar. Along here we have the neutron energy, which is pretty much how quickly these neutrons come flying out whenever we have a reaction. And along here we have the basically what's called the capture cross section, which is made of barns, which is a unit used by nuclear engineers. It's about 10 to the minus 24 centimetres squared, if I remember correctly. But this can be thought of as analogous to the probability that we will have yet another reaction once the neutron hits it. So you can see that when it's going really fast, there's not much chance that it will hit, that it will cause another reaction. Whereas when we slow it down, we can see that there's a much higher chance that we will then be able to create more reactions. So what we use to slow this down from here to here is the moderator, which, as I mentioned before, in a light water reactor is just water. We'll get on to how it works in other systems. Now, of course, when the Navy had this submarine, which was nuclear powered, the Air Force came along and said, well, we want one of those as well. So the experiment was designed, there was an experiment designed for an aircraft reactor experiment. Luckily for everyone, the invention of intercontinental ballistic missiles meant that the US Air Force no longer needed nuclear powered aircraft. So that didn't really hang around for very long. However, the scientists who were working on that thought, well, let's just take that technology, stick it on the ground, and see what happens then. So they came up with this molten salt reactor experiment. There's a fella working on it up there, just a scan. And again, this was based on a liquid fuel. So there's a few advantages or a few different things you can do with liquid fuel. Firstly, what they would do is use a molten salt, dissolve the fuel into it, so it looks something like this, and then we use this to pump around as the liquid instead of using something like water. Now, there's different fuels you can do with that. You can use thorium, you can use uranium, or you can use the spent nuclear fuel as well. Now, if you look at the thorium up here, so that's thorium-232. When you look at the top here, so you can't really see those arrows, but this cycle goes around this way. Now, thorium-232 is ideal for this. You don't need to enrich it, you don't need to do anything to it. However, to get this process starting, you do need some fissile material, so something like uranium-233 or uranium-235. Uranium-233 is not something you really want to be handling at any point. It's really quite dangerous, so quite often you start this cycle off with uranium-235. Now, so here's a schematic of molten salt reactor and how it works. So this is just the load loop, which has a couple of extra bits on it, but we won't worry about that for the moment. We'll just look at how the core works. So instead of pumping the water around, as I was saying before, we've got this liquid fuel which is being pumped around, and the thing which remains static in the middle is the moderator. So typically that would be something like graphite, and that will just live in the middle there with the salt being pumped around, and then that heat then gets generated, passed into a heat exchanger, into a secondary loop, which has another molten salt coolant in there, and then that gets carried off to the load loop. Now you can see we also have something like a chemical processing plant here, so it allows us to siphon off the fission products and whatnot. Because it's liquid, of course, we can chemically separate this all. And then another feature that they added here is an actively cooled freeze plug. So what happens is the energy or the power, when the power's running, this is actively cooled, so such that this is frozen. Then if the power shuts off, then this gradually starts melting, and then all the fuel salt gradually gets dumped into these dump tanks here, where it can be chemically separated, so that it's no longer radioactive, well, no longer radioactive, no longer is fissioning. Okay, so there's again a couple of advantages of the liquid salt fuel. Firstly, negative temperature coefficient, which is due to the volumetric expansion as the heat increases. So that means that as it gets hotter, it starts being less radioactive, which is a very useful feature. It means that overheating is actually very difficult to do. We also have decay heat is one of the main issues as well in solid fuel reactors. Basically, when you turn the whole thing off, it's still going to be still reacting and making decay heat for quite a while. Whereas that's really quite easily manageable in liquid salt reactors. As well as no pathway to explosive chemicals like we had earlier with the water, and which can end up with hydrogen. Okay, in terms of losing the coolant, you can't really do that because it's bound with the fuel. So you could lose the coolant, but then you lose the fuel as well. So the two are not separable. So you're not going to get a point where you have this fuel which isn't cool. Operates at low pressure, which is another great advantage as well. We're talking about typical domestic plumbing pressure. not the 180 odd bar that we have in a typical nuclear plant. High operating temperature range as well, which is exactly what we want for generating energy. And of course it allows chemical processing. Now this could be in an outboard chemical processor, as was demonstrated in that last schematic, but typically one of the things we do is sparging the neutron poisons. So we have things like xenon and krypton building up, which I was talking about with the solid fuels, but when they crack and they start disappearing, in this case we can actually just start bubbling something like helium through it, and then they will dissolve out into the fluoride salt, so they are then chemically bound to the fluoride. So again, a few more advantages, because we've got ionic bonding here, so it prevents radiation damage. This is sort of thing I was just talking about here. So these various fission products are chemically bound into the fluoride salt. We have high volumetric heat capacity as well, which means we can build smaller cores with them as well. Uniform temperature gradient. This demonstrates what I was talking about earlier. This curve here is with what we have with a solid fuel pellet. So if we look at the middle and then the temperature as we go towards the edge of the fuel pellet, it drops quite dramatically. Whereas of course if we have liquid fuel, it's just evenly dispersed, so it makes it a lot easier to predict, you know, where the temperature is going to be. Now, because we've got a higher heat transfer as well, that means we have a higher thermal efficiency, which means we can use a smaller turbine. So because typically in nuclear reactors you'd have a much larger turbine than you have in a gas or coal plant. And as I discussed, obviously the pellet cracking doesn't even come into it because there's no pellets in there, or meltdown, of course, there's no such thing because it's already designed to be liquid. Now typically all this stuff within the red box that I've added will all live within one particular sort of containment area, so that the fuels aren't exposed to the outside world. Of course you'll have multiple barriers, but these will all typically be within a single barrier, so that there's no actual radioactive fuel exposure to it on. Okay, so in terms of the advantages of the salt, that allows for several advantages when we start using the salt and start putting it into a reactor. So we can now have a much more compact unit, which means we can start building them in a factory and shipping them to site and start assembling them, which makes things a lot cheaper and easier. We can also build them underground as well. All the designs I'm going to show you are all designed to be underground. So we can also have centralised decommissioning as well, which makes things a lot easier. So we can decommission and recycle things all in one place rather than taking everything to the site. Again, we can put these things, we're a lot more flexible about where we can actually put these things. It's actually physically smaller footprint as well. Also a lot easier to shut down. You can, all of these, every one of which we're going to talk about later, is all described as being walk-away safe. Typically with a freeze plug, but there are also other ways of doing it as well. And they're all load following as well, which means that unlike a lot of conventional nuclear, you can say I'd like more power please, and you do it, and within a few minutes you've got more power, or I'll have less power please, and typically again you'll have less power, so they can go up and down quite a lot. As I mentioned, typically about 90% fuel burn up, sometimes more. We get rid of these neutron poisons as well. Basically, we still will end up with nuclear waste at the end of this, but it will be significantly less volume than there was to start with. It will also be more radioactive, but for a significantly significantly shorter time. Typically, the order of a couple of 100 years rather than thousands of years. So all of these, I've mentioned all these advantages, lead to lower cost. Ultimately, a lot of these guys claim that it will end up being cheaper than coal, which is the main point, because then, of course, it's economically advantageous to build one of these rather than to build a coal plant. The reason I put it in inverted commas is because there is still development work needed, so we'll need to throw a bit more money at this before we can start getting to that point. But ultimately, the goal is to be cheaper than coal. So I'm just going to take you through some of the reactors. So Flybe Energy, which is named after the salt that they use, which is a lithium fluoride beryllium mix. This is a US design model, works as a breeder reactor, so the thorium fuel cycle we saw earlier, it uses that, and the reason it's called breeder is it ends up with more fissile fuel than you actually put in. So this works on the thermal spectrum. If you remember that graph I showed you earlier with the fast and thermal spectrum, and it's moderated by graphite. There's a bunch of statistics which you've got on your sheets there, so I won't dwell on those too much. But this is what the core looks like. So we have the fissile material pumped through the middle, and then versatile stuff pumped around the edge of the core. We've got some neutron reflectors here. Now this one relies quite heavily on its chemical processing, so I'm not going to go through all this, what this does, but it removes various parts of what needs to be in the fuel and what's poisoning the fuel, what's stopping reactions from happening. But the other thing they claim is that they are going to sell off these other products, such as desalination from the process heat, and then the various other fission products, which is as a result of their chemical processing. So Thorcon, this is another one. This is design number 2. American design again. Now this one works on a 4-year life cycle. So we have these various modules. This is one module here. It consists of two of these cans. There's 1 can, 2 cans there. Now what we have here is they stick 2 of these cans. Well, they stick 2 of these cans in there. They run one of them for 4 years. Then they shut it off and they switch on the other one. And the other one sits there for 4 years, just decaying, just losing all its heat, and then it gets taken away and reprocessed essentially. So the whole thing's a sealed unit, and that resolves a lot of issues for decommissioning. The other thing which they want to do is they claim that they can knock out 100 of these every year. So that's 100 1 gigawatt electric stations. And the way that they do that is because they have a background in shipbuilding. So, as they say, these things are a lot smaller, have a lot less complicated parts than a ship, and they manage to knock out about 100 of these a year anyway. So, it shouldn't be too much harder to do one of these. So here's a look at the core. It goes around clockwise in that direction. There's various salt compositions that they have, and this actually runs of 3 loops before it gets to the power as well. We've got this other thing which hides inside the module, inside the silo, is where the off gases go to. So they're stored in there as well. And that's an example. So we actually have a high pressure one and a low pressure one within the same module. So there's a certain time which goes on between when they get transferred from there to there. Okay, so this one's the Seaborg waste burner. This is a Danish design. As you can see, they're very keen on concrete. They basically live in a big ditch underground. These things which are akin to shipping containers. This is used as a dump tank. That's the where the core is, and basically they put these massive slabs of concrete on there, and the whole thing lives underground. No one's allowed near it during the whole operation. So this one runs off spent nuclear fuel, works in the thermal or epithermal spectrum, and again relies on chemical processing. So it's got a flame reactor there. Doesn't really tell us very much. Another thing about this one, has this overflow system here, so much like a sink or your bath at home. So it's got an overflow. So if anything, if this tank ends up getting full, then it will go straight down into the dump tank. So that remedies quite a few of the predicted failure modes. Here the graphite logs as well. There's one graphite log, and they'll be collected together in a core like that. Another thing they also do to avoid weapons proliferation is they don't at any point separate the neptunium from the plutonium, which means that you basically can't use that as nuclear weapons fuel. Okay, here's another one here, terrestrial energy, Canadian system. This one works in thermal spectrum, graphite moderated as well. Similar to the Thorcon one, similar principle where you'll have one core running and then you have another one spare or cooling down. So it was a 7-year cycle rather than a 4-year one. Now these ones are designed to fit on the back of a lorry, so again you can be shipped out to various locations, although the larger cores, so they have them in 80, 300 and 600 megawatt thermal. The larger ones will need to be assembled in-house. Now the interesting thing about this one, rather than having a freeze plug, they have this outside wall of salt, and during normal operation it's solid, but if this starts overheating, if one of the motors burns out or some such, then this will start melting. So we've got latent heat transfer going on throughout this wall of salt, and then we have convection as well, and it's also cooled passively by these water pipes running on the outside. So the entire thing is, the entire core is integrated and just needs to be, the whole thing just lifted out, swapped out. And we've got this one here, transatomic, and a couple more. Transatomic power. This one uses a different moderator, zirconium hydride, and it also uses lithium fluoride based salt, which means, I'll explain how in a minute, but means we can get low enriched uranium down to 1.8%. And now typically you want about 5% for a nuclear plant. So that's quite a significantly lower amount of enrichment needed for the fuel for this sort of plant. I'll just show you this graph. Here's the energy along here, much like we saw earlier with that graph before, but we're looking at the moderator now instead of the fuel. So this blue line here is zirconium hydride, and you can see we've got peaks here in the thermal spectrum and in the fast spectrum as well. That means that we can start burning up fuel down here and down here. So even before it's got moderated, then we're burning up some of the fuel. This allows us to get rid of some of the actinides, which are some of the more dangerously radioactive elements as well. Right, the last one we've got here is Moltex Energy, which runs off a completely different kind of system. This runs off spent nuclear fuel. The main coolant salt is actually sodium chloride, which is easy enough to get your hands on. But this one, what they have is these fuel tubes here, which stay static, and they're filled full of liquid tubes. And then they pump this coolant around here in a big bath. And then we have the separate load loop just running out of that. So there's a lot more, there's a lot less moving parts. The impellers here as well have the advantage that they're just pumping around molten salt, which isn't radioactive. We've got these fuel rods up here as well, so you can see we've got at the top there these valves which allow things like xenon and krypton to be buttoned out, and if anything they just end up kind of falling into the bar salt here. They also put zirconium in here as well to prevent corrosion. So overall it's a much simpler system, and out of all the ones which we looked at in the report, we decided that this one is going to be the one most suitable for immediate deployment in the UK. Not as online refuelable as some of the rest of them. Of course, the other advantages that we can with liquid fuel is we can just kind of inject it into the system. This one, because we are looking at fuel rods, we have this sort of system where we end up shuffling them around, but it's really not a huge effort, and it's a lot quicker and easier than it is in existing nuclear power stations as well. So, with all these advantages, you might ask yourself, well, why is no one doing this? Of course, the answer is that they are in China. If there's one place you were going to guess that they were going to do it, then I suppose that would be it. So they have a timeline whereby they're looking to build commercial, certainly. This MSR solid fuel means that it's cooled by by molten salts, but still using solid uranium fuel. Whereas the bottom one here is we're looking at using liquid fuel salt as well. So you can see the timeline here, having a proper commercial one by 2035 for the solid fuel, and then even still having a demo reactor by the same point with the liquid fuel. So now, why are we not doing this? Well, there's a few obstacles. Licensing is a big one. I was explaining to the gentleman earlier. To get a site license costs lots of money, takes a lot of time. To get even a single new material license for nuclear also takes a lot of money and a lot of time. Same with changing designs as well. Anything to do with any time you need to get anything licensed in the nuclear industry, it will take lots of money and lots of time. People still need to put capital investment into this as well. Companies or independent shareholders are generally not so keen. They prefer to wait for the government to lead, and of course the government are waiting for the industry to lead as well. So we're in a bit of a stalemate there. Of course, people have already got their existing interests or investments in the current nuclear technology as well. And of course, a lot of people still don't really know so much about this technology either. So those are all reasons that we're not currently doing this. So we're spending a lot of time trying to get the word out, trying to raise awareness, so that this sort of thing can start happening. So again, just to summarise what we found from the report, they're both technically and economically feasible to build a pilot plant at this point. We do still need development in terms of the chemical processing and corrosion resistance, but other than that, we're pretty much ready really today to start building any of these systems at a sort of pilot scale. I've given you a list of further reading there, but that's some nice pictures for you to look at. And are there any questions? That gentleman over there.
How dangerous do you think it is to have a liquid fuel